Okay, so
Yeah.
ready to dive into something kind of sci-fi today. Fusion power. We're talking clean, limitless energy, the kind that could seriously change the world. And today, we're focusing on a country that's, well, they're making some huge, huge strides in this whole fusion thing. South Korea.
They're really leading the charge, aren't they?
Yeah, you might
Yeah.
be thinking, fusion, isn't that like decades away? But here's the thing. South Korea is delivering real, tangible pieces of a working fusion reactor. Right now, like they've just finished their part in building these gigantic vacuum vessel sectors for the ITER project over in France.
Oh, yeah, ITER.
Huge, right? We're talking sectors that weigh thousands of tons, with kilometers of welding in each one. It's pretty mind-blowing.
It's an incredible feat of engineering, that's for sure.
So in this deep dive, well, let's explore exactly what South Korea has achieved and what it all means for the future of fusion energy. Just imagine like having a miniature sun right here on Earth.
It's a pretty wild concept when you think about it.
It really is. One of the things that really jumped out at me was that South Korea just finished delivering all 4 of the vacuum vessel sectors they were assigned for ITER. And get this, they actually ended up building 2 more than they originally agreed to.
It's fascinating, isn't it?
Yeah.
Really shows their commitment to this whole project.
Yeah, it really does.
But before we go any further, maybe we should kind of back up a bit and explain what ITER actually is. For, anyone who might not be familiar, ITER stands for International Thermonuclear Experimental Reactor.
Right.
Basically, it's this massive international collaboration trying to, well, prove that fusion power can actually work.
Exactly. So ITER is this huge undertaking, and this vacuum vessel, it's like the heart of it all. This massive structure, it holds the superheated plasma where, all the fusion magic happens. So what exactly makes this vacuum vessel so special, and why is South Korea's contribution so significant?
Well, imagine you're trying to contain a star. That's essentially what fusion is, right? You need an incredibly strong airtight container to hold that superheated plasma.
Yeah.
Which, by the way, can reach temperatures hotter than the core of the sun.
Wow.
And this container, it has to operate in a high vacuum environment. It's like a gigantic high-tech thermos for a star.
Whoa. Okay. That is a pretty intense image. 5,000 tons, 9 sectors, 44 ports. It boggles the mind. And they had to maintain like millimeter precision across this whole massive structure. What were some of the biggest hurdles South Korea had to overcome to pull this off?
That's a great question. Building something this complex, it's really an engineering feat of epic proportions. I think one of the biggest challenges they faced was the welding of the sectors. Remember, these things are huge.
Yeah.
And the welds have to be absolutely perfect.
To withstand all that heat and pressure.
Yeah.
Right.
Exactly. The extreme temperatures and pressures inside the reactor.
Yeah.
South Korea, they actually had to develop these innovative welding techniques and technologies, really, just to meet these incredibly demanding specifications.
So they essentially pushed the boundaries of what was possible with welding.
We really did, yeah.
Wow. So not only did they build these massive components, they also had to invent new ways to actually put them together.
Right.
That's dedication. And on top of their initial commitment, they took on 2 extra sectors. I mean, some might see that as going above and beyond. What do you think motivated them to take on that extra work?
I think it's more than just dedication. It's strategic, I think. South Korea, they clearly see fusion as a key technology for the future. By taking such a leading role in ITER, they're really positioning themselves as a major player in this whole global fusion energy landscape.
That makes sense. So it's not just about, contributing to a global project. It's about becoming a leader in a field that could, revolutionize the world. Now, we've talked about South Korea's role in ITER, but they also have their own fusion reactor, K-STAR, which has been breaking records. Before we get into that, can you give us a little background on K-STAR and what makes it so special?
Sure. So K-STAR, it stands for Korea Superconducting Tokamak Advanced Research. And just like ITER, it's a tokamak, but on a smaller scale. It's essentially a test bed for a lot of the technologies being used in ITER. It's kind of like a smaller experimental version of ITER, you could say.
Okay, so like a smaller test version. And you said it's been breaking records.
Yeah. K-STAR, it's been incredibly successful at pushing the limits of what we can do with fusion. Back in 2021, they achieved something amazing. They maintained a high-temperature plasma for a full 20 seconds, a world record at the time.
20 seconds. I mean, I know that might not sound like much, in everyday life, but I'm guessing in the world of fusion research, that's a pretty big deal. What makes it so hard to keep a plasma going for that long?
It all comes down to controlling something that's incredibly hot and unstable, Plasma, it's essentially a superheated gas where like the atoms have been stripped of their electrons.
Right.
And it behaves in some really unpredictable ways. It's almost like trying to hold lightning in a bottle.
Wow, I like that analogy.
Yeah, and the longer you can keep that plasma stable and at just the right temperature, well, the closer you get to achieving a sustained fusion reaction, that holy grail of fusion energy.
So every second really does count. And K-Star hitting that 20-second mark, that was a major win for the technologies and approaches they're using, both in K-Star and in ITER, right?
Oh, absolutely. K-Star has been so important in proving that a lot of the concepts they're using for ITER, that they actually work. It's given scientists and engineers a lot more confidence as they move into the final assembly and operation phases of ITER.
Right. Now, K-Star's success it's definitely encouraging, but I imagine some critics might say, well, sure, it works on a smaller scale, but what about when you scale it up to something as massive as ITER? What do you think about that?
That's a fair point, yeah. ITER is significantly larger and way more complex than K-Star, and scaling up, it always presents new challenges. But even so, the success of K-Star has provided invaluable data and insights, and it's stuff they're using directly to inform the design and operation of ITER. It's almost like having a really detailed roadmap, You can kind of prove that you can navigate the terrain before setting out on this much longer journey.
So in a way, K-Star is paving the way for ITER's success, which brings us back to ITER. Now that South Korea has delivered its vacuum vessel sectors, what are the next steps for the project?
Well, ITER it's currently moving into its final assembly phase. All the different pieces, many of them built in different countries all over the world, they're all being brought together in France. And this assembly process, it's incredibly complex and challenging. Imagine like a giant three-dimensional puzzle, but with pieces that weigh thousands of tons each, and you need millimeter precision.
Oh, wow. It's mind-boggling just to think about the logistics and coordination involved. Just getting those vacuum vessel sectors from South Korea to France, that alone must have been a huge task.
Oh, you're actually right. They had to use specially designed ships and overland transport routes just to move these massive components.
Yeah.
There's a true global effort just to get all the pieces to the assembly site.
And now putting it all together, it's almost like building a giant spaceship.
Yeah, that's a great analogy. The level of precision and coordination required, it really is similar to aerospace engineering.
So it sounds like we're getting closer and closer to seeing this massive machine come online. And it's not just about assembling the physical parts, right? There's a whole other layer of complexity when it comes to actually getting this thing running, actually generating that fusion reaction.
Exactly. Once the assembly is done, the next phase is commissioning and testing. So they'll need to, fine-tune the magnets, get those vacuum systems running perfectly, and slowly, carefully ramp up the power to the plasma. It's going to be a long and meticulous process.
That's where things start to get really interesting. What kind of hurdles do you think they'll run into during this commissioning and testing phase? Like, what are the biggest challenges they'll face in actually creating a sustained fusion reaction?
I think one of the biggest challenges will be, well, it goes back to controlling that plasma. Like I said before, plasma, it's incredibly hot, incredibly unstable. Maintaining those perfect conditions for fusion to happen, the right temperature, density, and confinement time, it's extremely difficult. And then there's also the challenge of, managing the tremendous heat and energy that's released during fusion.
It sounds like they're essentially trying to tame a star. Right. What kind of safeguards are in place to, to make sure everything is safe, for the people involved, for the environment?
Safety is absolutely paramount in a project of this scale, yeah.
Yeah.
ITER has multiple layers of safety systems. They're all designed to, contain the plasma, manage all that heat and energy, and really prevent any potential accidents. They've incorporated some really state-of-the-art diagnostics and monitoring systems to, detect any issues, anything unusual, and shut down the reactor if they need to.
Okay, that's good to know. It sounds pretty reassuring. So given, just how complex this whole project is, I'm guessing collaboration is going to be key to overcoming all these challenges.
Oh, absolutely. The success of ITER really depends on the expertise and collaboration of scientists and engineers from all over the world. It's really a testament to what we can achieve when we work together towards a shared goal. And it's not just about the technical stuff either. It's about the human element too. The communication, the coordination, and just that shared passion for advancing science and technology.
It really is remarkable. It's amazing to see how much progress they're making. It feels like, like we're on the edge of something truly groundbreaking. But before we get ahead of ourselves, let's take a minute to recap what we've learned about, South Korea's contributions. And what their success with K-Star means for the future of ITER. So looking back at everything South Korea's done, I mean, it's obvious they've made some pretty serious contributions to ITER.
Oh, for sure.
They delivered all 4 of those vacuum vessel sectors,
Yeah.
which, remember, those are part of that 5,000-ton structure.
Yeah.
And those required incredibly precise welding.
Yeah, it was an incredible undertaking.
And they didn't stop there.
Nope.
They went above and beyond and built 2 more sectors. That's a massive undertaking,
Yeah.
like engineering-wise, logistics.
I mean, don't forget those vacuum vessel sectors. They're just one piece of this whole puzzle. South Korea, they've also been a big part of developing some other really crucial components for ITER, like superconductors and thermal shields.
Right.
They're clearly committed to, making fusion a reality.
Right.
And their expertise is evident in everything they've done.
It really is impressive to see them so invested in this technology. And then you've got K-Star, their own fusion reactor, which, well, it's been breaking records, pushing the boundaries of what's possible. What's really cool to me is how their success with K-Star is like, it's feeding directly into ITER. It's almost as if they're doing like a smaller scale test run before the big show.
That's a great way to put it. K-Star has been so valuable as a proving ground for a lot of the technology and ideas that are being used in ITER. Like that record-breaking 20-second plasma achievement. That was a huge confidence boost for the whole fusion community. It showed everyone that the physics behind fusion power, they're sound, and that, sustained reactions, they're within reach.
Yeah. So in a way, what South Korea is doing with K-Star, it's kind of giving us a peek into the future of fusion energy.
Yeah.
What they've learned, what they've demonstrated on that smaller scale, it's informing the design, the construction, the operation of ITER. It's a pretty amazing example of how scientific progress can build momentum and lead to even bigger breakthroughs.
Exactly. And it brings us back to something we talked about earlier. Like, if ITER works, if it's successful, how will fusion energy change things geopolitically? Will it bring countries together, greater cooperation? Or will we see competition for this new power source?
It really is a question worth thinking about. I mean, on the one hand, fusion, it has this potential to unite nations, everyone working towards a common goal. The pursuit of clean, abundant energy for everyone. It's something that could go beyond borders, something that could really foster collaboration in science and technology.
But at the same time, having control over such a powerful technology, that could become a point of, disagreement.
Mm-hmm.
Countries might fight for dominance in fusion research, fusion development, which could lead to a whole new kind of energy race. The stakes are pretty high. And the potential for both cooperation and conflict, it's real.
It's a fascinating thought and something we really need to be careful about as fusion technology gets more advanced. It shows how important it is to think about, not just the technical side of fusion, but also the social and political implications. We have to be ready for the huge changes fusion could bring.
I agree. Fusion energy, it's not just a technological thing. It's something that could change the world, change humanity. And, as we've seen with South Korea's work on ITER and their own progress with K-Star, they're right at the forefront of shaping this future.
This deep dive, it's really been incredible. We've explored this world of fusion power and the crucial role South Korea is playing in making it happen. We've talked about the mind-blowing engineering behind ITER, their achievements with K-Star, and just the potential fusion has to reshape, well, everything. If this has you as captivated as we are, we really encourage you to keep learning, to keep exploring. This is really just the beginning, and we can't wait to see what the future holds for fusion energy.